Okay, time for exercises. So first one, VW Banach spaces and T in LVW compact. Let Xn weakly converge to X in V. Show that Txn converges to Tx in W. So a compact operator converts a weakly convergent sequence to a norm convergent sequence in the range. Okay, so that is the powerful property of compact operators. So solution. So weakly convergent implies bounded. We know that. So let norm Xn be less than or equal to M, and then we know that T of BV 0M closure is compact in W. Okay. So implies there exists a convergent subsequence T and K, T, X and K. But Xn goes to X weakly, X and K also should go to X weakly in V, implies T is weakly continuous because the continuous linear operator. So Tx and K converges weakly to Tx. So this implies that limit, so Tx and K converges in norm and it converges weakly to Tx, therefore Tx and K converges in norm to Tx. Okay, so this happens for a subsequence. So given any subsequence Xn K of Xn, there exists a further subsequence XnKL such that Tx and KL converges always and the limit will always be Tx. So the limit is irrespective of the subsequence chosen, and I've already mentioned this fact before. In a topological space, if you have a sequence such that you have a subsequence, any subsequence, there's a further subsequence which converges and the limit is independent of the subsequence, the limit is unique, then the entire sequence converges. So this means that Txn converges to Tx. Okay, so this proves, so this, you see, the topological trick is very, very important and very useful and very trivial to prove. Okay, 2. So A, VW Banach spaces, V reflexive, T in LVW. Let Xn weakly converge to X in V. Imply Txn converges in norm in W. So we are making this assumption, whenever there is a weakly convergent sequence, it converts it into a norm convergent sequence. Then show that T is compact. So this is the converse of the previous problem, only we are now assuming that V has to be reflexive. So solution, so BV closed unit ball in V. Okay, so Xn is any sequence in B. V reflexive implies there exists Xn K and X such that Xn K converges to X, and this implies that Txn K converges to Tx, and therefore given any sequence xn, the subsequence is Tk converge to Tx, therefore BV, T of BV closure is compact, that is T is compact. Okay. B, not true if V is not reflexive. So let us take example. So you take identity map from L1 to L1. Okay, so this is not compact because L1 is infinite dimensional, so the identity map is not compact. Okay, so but if xn converges to x weakly in L1, this implies xn converges to x in norm. This is Schur's lemma. Therefore, this condition is satisfied, but the mapping is not compact. So the reflexivity is important in this. Okay. 3. A, V reflexive and T belongs to L of V L1, then T is compact. So solution. So let xn be bounded in V. So there exists a weakly convergent subsequence. So xn k and this implies that Txn k is weakly convergent in L1, implies Txn k is norm convergent in L1, again by Schur's lemma, and this implies that T is compact. So any bounded linear operator from a reflexive space into L1 is automatically compact. Okay. B, W reflexive, T belongs to L of C0 W, then T is compact. So solution. So T belongs to L of C0 W. So this implies that T star belongs to L of W star C0 star is L1, okay, and W reflexive implies W star is reflexive, and therefore by A, T star is compact, and then we know that implies that T is compact. Okay, so 4, H infinite dimensional Hilbert space A in LH such that compact and such that AXX is strictly positive for x not equal to 0. Show that there does not exist alpha positive such that AXX is greater than or equal to alpha times norm x square for all x in H. So solution. So we have that En orthonormal set in H. It may or may not be a basis depending whether H is separable or not, but by the Bessel's inequality we know that En always converges weakly to 0. Therefore, AEN should go strongly or in the norm to 0. So you have that AEN, this goes to strongly to 0, this goes weakly to 0, and therefore this has to go to 0. Okay, and suppose you have then AEN greater or equal to alpha times norm En square, which is 1, and this is strictly positive, and that's a contradiction. Okay, therefore you cannot have a. Now if H were finite dimensional, then of course there exists an alpha such that AXX is greater or equal to alpha times norm x square. So a positive definite operator always has this property, positive definite matrix, because if you have AXX on norm x equal to 1, x going to AXX is continuous, and norm x equal to 1 unit sphere is compact, and therefore there exists, it attains its minimum. Okay, so therefore there exists x naught, norm x naught equal to 1 such that AX naught x naught equals minimum of AXX, norm x equal to 1, and call this as alpha, and then you have AXX is greater or equal to alpha times norm x square for all x, because you take x by norm x and then you will get this. Okay, so in finite dimensions this certainly happens, and that is why we are trying to see if it happens in infinite dimensions, but it does not happen in infinite dimensions. Okay, 5. V Banach and T in LV compact. Let S belong to LV, then S of I minus T equals identity if and only if I minus T times S equals identity. In this case, show that. Okay. In this case, show also that I minus T is invertible, and that I minus T inverse is compact. Okay, this is almost very trivial. So solution. Okay, so let S of I minus T equal to identity, and then you assume that let I minus Tx equal to 0. So this implies S of I minus Tx is also equal to 0, but this is equal to x, and therefore null space of I minus T is singleton 0. But then T is compact, and therefore this implies that range of I minus T has to be the whole space V. So I minus T is 1, 1 continuous and on 2, and therefore I minus T is invertible, and you have S equals I minus T inverse, and this implies that I minus T times S equals identity. Conversely, if I minus T times S equals identity, then X equals I minus T Sx for all x. This implies that range of I minus T is the whole space V, because every x can be written as I minus T of something. Okay, and therefore null space of I minus T has to be 0, 1, 1 if and only if on 2, because T is compact, and therefore this implies 1, 1 on 2 continuous by the open mapping theorem. This means invertible, implies S equals I minus T inverse, and that implies that S times I minus T times I equals identity. And now I minus t inverse is nothing but I minus s, okay, and this is equal to I minus t times s minus s, okay, and that's equal to s into I minus t minus identity, which is minus t, and composition of a compact operator in any other, this is compact, and therefore this is equal to this also compact. Six, let H be a Hilbert space and T in LH compact. Then norm T equals maximum over the unit sphere equal norm Tx. We know that it is the supremum, and if you have a compact operator, then it is in fact the maximum. So solution, norm T is the sup of norm x equal to 1, norm Tx. So let norm xn equal to 1, xn maximizing sequence. That means norm Txn converges to norm T. You can always find because it's a supremum, therefore you have. Then xn has norm 1, it's bounded, so you have a subsequence xnk which converges to x, and since it's weakly convergent, you have that norm x is less than or equal to 1. Okay. Then Txnk converges in norm to Tx, therefore norm Tx is the limit of norm Tx and k, which is equal to norm T. Okay. So and you have that norm x is less than or equal to 1. So norm T is therefore less than or equal to norm Tx by norm x, because norm x is less than or equal to 1. So I am dividing by something smaller than 1, so this becomes bigger, but then this is always less than or equal to norm T. Therefore norm T equals norm of Tx by norm x, which is norm of T of x by norm x, which has norm 1, and therefore you have that it is in fact the maximum over the unit sphere, maximum over the unit ball, whatever you want. Okay. So 7, let Hi, I equals 1, 2, 3 be Hilbert spaces. Assume that H1 is continuously embedded in H2 and it is continuously embedded in H3. That means these are subspaces and the inclusion maps are continuous. Assume that the inclusion H1 into H2 is compact. Let epsilon be positive. Show that there exists a C epsilon which is positive, such that for all u in H1, which is in all the three spaces, we have that norm u in H2 is less than or equal to epsilon times norm u in H1 plus C epsilon times norm u in H3. Okay, such inequalities are very useful in study of partial differential equations, and the compactness helps you to get for any small epsilon you can put here, and then you compensate it by putting a big constant here for the other function. Okay, so this is solution. Assume not. Then whatever constant you put here, you can find a vector which violates this inequality. So for every n in n, there exists a un in H1 such that norm un in H2 is strictly bigger than epsilon times norm u n in H1 plus n times norm un in H3. So I am taking C epsilon as n, and therefore for every such n I will have a violation, and therefore this is 2. Now I can divide throughout by norm un in H2. So without loss of generality, assume norm un in H2 equal to 1 for all n. So otherwise you just divide through and that will give you that. So you have 1 is bigger than epsilon times norm un in H1 plus n times norm un in H3. So this says that norm un in H1 is less than or equal to some constant which is equal to 1 by epsilon, if you like, and then norm un in H3 is less than 1 by n, so this goes to 0 as n tends to infinity. So there exists because the inclusion H1 to H2 is compact, so we have to use that hypothesis. So there exists subsequence UNK such that UNK converges to U in H2 and weakly in H1. And it also therefore automatically converges to U in H3 also. And but UNK in H3 goes to 0, so this implies that U equal to 0 because of this fact. So you have UNK weakly goes to 0 in H1, UNK goes to 0 in H2 and goes to 0 in H3 as well. But norm UNK in H2 equal to 1, and therefore you have a contradiction to this. Okay, so therefore there exists such a constant. So okay.